Hello there, everybody. In this video, we're going to be looking at another partial differential equation. And this is along the series of what are partial differential equations, and then later in the series, we'll look at numerical analysis on partial differential equations. So for this one, we're going to be looking at kind of one of the two very common differential equations called the wave equation. You probably have already watched the video on developing the diffusion equation, also known as the heat equation. So in this one, imagine that we have a guitar string, and that guitar string is stretched taut and then plucked. So initially we have our string here, and then at some point we pluck the string, right? We pull part of the string up. Oops, let's get that to autofocus there. Come on, buddy. Okay, it'll come back. At some point, you pluck the string up and let go. Well, if we zoom in close enough, right, part of the string just looks like some curve. Come on, focus. Okay, there we go. Sorry about that. Hopefully you fast forwarded through that. So if we take some tiny, tiny little slice of the string and blow it up this way, we've got some curve. And I'll say at the left side and at the right side of the curve, there's going to be different tensions on the string, right? So this particular string, let's do it this way. So I've got the curve here. I'm going to draw a tangent vector here. I'll call this tangent left. And I'm going to draw a tangent vector here. I'll call this tangent right. I'm sorry, yeah, these are basically the tensions on the string. Now we can split this into horizontal and vertical components for each one of the tensions, right? So for the left, we've got, this is going to be TL times sine of this angle. I'll call that theta left. And here I'm going to call theta right. So I can get the horizontal and vertical components of those particular tensions. Now, from here, we really just need some basic physics. What we're going to say is that force equals mass times acceleration. The force is the tension on the string, and the mass times acceleration, well, let's see here. If I take u to be the position of the string, right? Acceleration is the second derivative with respect to space, and the mass is the density of the string times the length. So if I take this thing to be length delta x, so let's just mark that. I didn't leave myself enough room here. Let's say that's a length delta x, and rho is the density, which is going to be mass per unit length. Okay, so now what I have is that tension is equal to rho delta x times acceleration. But now I just need an expression for the tension. Well, the tension that I have in the spring is really, let's do right minus left. So I'm going to do tension on the right-hand side, sine theta r, minus tension on the left-hand side, sine theta L, is equal to rho delta x times acceleration. Well, let's stop and think about the physics. This is the difference in tension in the vertical direction. So I've got tension pointing up and tension pointing down, and the difference in those is what's going to cause this string to vibrate up and down. Now I'm making an assumption here. Let's assume that I'm not going to have any wiggles left and right. I'm only going to have wiggles up and down. And this is the only thing giving us a force in the vertical direction. So what I also know then is that if I don't have wiggles left and right, on the right-hand side, my horizontal component has to be equal to the horizontal component on the left-hand side. I'm just going to say, I'll call that t. That's just going to be constant. So now what I can do is I can take my first equation. This is really F equals ma, Newton's second law, and divide through by my constant tension. But if I do it in just the right way, I can have this tr, oops, no tr, forget that I wrote that. I can have tangent of theta r minus tangent of theta L is equal to rho delta x over the constant t times the acceleration. Okay, now think about how I got the tangents. Sine over cosine, this over this particular constant. Since these are all the same, I divided everything through by the same thing. But now notice that this is just, that is the slope over here on my curve. That is the slope over here on my curve. So that is ux at spatial point tr. Oh, shoot, I made a mistake. Oh my goodness gracious. Oh my goodness gracious. I hope you guys caught me on this. None of those should have been derivatives with respect to x. That's a derivative with respect to time. We're talking about acceleration, people. Come on. I really hope you guys caught that and you just let me fly with it until I caught it myself. Okay, now back to this. That guy is just a slope on the right. That guy is just a slope on the left. So this is going to be at, I'll say at the right-hand point. This is ux, we'll say at the left-hand point, equals rho delta x over t times my acceleration. But this right here, this difference, if I divide that by another delta x, that becomes, looks like a second derivative. Okay, so if I divide that through by a delta x, and comparably divide this through by a delta x, getting a cancellation there. All right, what I have now in the limit, right? So I'm thinking in the limit as delta t heads to 0 and as delta x heads to 0, I actually get a differential equation. And if I rewrite this, the acceleration is equal to t over rho times the concavity. And this in particular, we usually just call some other constant, and that has to do with the tension in the string. And this is what's known as the wave equation. This is really our second partial differential equation. So in the diffusion equation video, you saw that we had particles moving due to random Brownian motion. And in this case, we were simply just using Newton's second law, F equals ma. And we come up with a differential equation. Again, this is relating the position, partial derivatives of the position in space to partial derivatives of the position in time. And the story goes similarly for all other partial differential equations. There's some sort of physics or some sort of phenomenon we want to model, and we get some sort of relationship in terms of PDEs. So in the next video, we're going to look at what it means to do numerical analysis on PDEs.